Somewhere at NASA, right now, a command is being written. Just one. Once it's sent, it cannot be recalled, it cannot be edited, it cannot be tested first. It will travel for more than 19 hours across 13 billion miles of empty space before it reaches the machine it's meant to save. And if it's wrong, even slightly wrong, the most important set of ears humanity has ever placed beyond the solar system goes silent forever. The engineers who designed this command gave it a name. They call it the Big Bang. And the strangest part isn't the risk. The strangest part is why they're taking it. Because the machine they're trying to save has already told us something about the edge of our solar system that no one expected. Something that broke the models. Something that a senior scientist on this mission admitted out loud they still do not understand. This isn't a story about a spacecraft running out of battery. This is a story about the last working instrument at the frontier of everything we know, and a single irreversible gamble to keep it alive. Here's my promise to you. By the end of this video, you'll understand exactly what Voyager 2 measured at the boundary of interstellar space, why it forced scientists to throw out decades of assumptions, and why the next command NASA sends could be the difference between more answers and 25 years of silence. Stay with me. Because once the Big Bang is sent, there's no taking it back. Before we go further, if you want the real science, the verified data, the actual findings explained at the weight they deserve without anyone inventing a single thing the instruments didn't measure, subscribe. This is the channel where that drops first. Now, to understand what's about to happen, we have to go back. There are 2 spacecraft in interstellar space, not 1. 2, almost everyone knows the first one. Voyager 1, the golden record, the farthest human-made object ever built, the one that keeps making headlines. But there is a second machine out there, quieter, less celebrated, traveling in a completely different direction, sampling a completely different slice of the space between the stars. Voyager 2. And here's the first thing almost nobody tells you about it. Voyager 2 launched first, August 20th, 1977, 16 days before Voyager 1. The number in its name isn't a mistake. It reflects the order the 2 probes were expected to reach their targets, not the order they left Earth. Voyager 1 took the fast lane, Jupiter, Saturn, and then a hard turn up and out of the solar system. Voyager 2 was handed a longer, harder road. A route that let it do something no spacecraft had ever done before, and something that, nearly 50 years later, no spacecraft has ever done again. Voyager 2 is the only machine in history to visit all 4 of the outer giants: Jupiter, Saturn, Uranus, Neptune, every gas giant, every ice giant. All of them up close, with instruments built to read their atmospheres, their magnetic fields, their moons. At Uranus in 1986, it found 10 unknown moons and 2 new rings, and measured a planet tipped almost completely on its side, spinning at an axial tilt of nearly 98 degrees. At Neptune in 1989, the final planetary encounter of the entire program, it clocked winds screaming at more than 2,000 kilometers an hour, the fastest measured anywhere in the solar system at the time. And on Neptune's moon, Triton, it found active geysers, shooting material kilometers into a whisper-thin atmosphere on a frozen world at the edge of the planetary family. A spacecraft launched before the internet, before personal computers, before cell phones, designed to last 4 years. It's still transmitting, 49 years later. But none of that is the reason Voyager 2 became the most scientifically important spacecraft of this entire mission. The reason is a single instrument, and to understand it, you need to know about the day decades ago when Voyager 1 went blind. Both Voyagers launched carrying an identical set of 10 instruments, twins in every way. One of those instruments was the plasma science experiment. Its job was simple to describe and almost impossible to replace. Directly measure the plasma, the charged gas, flowing around the spacecraft, its temperature, its density, its speed. Here's why that matters. The edge of our solar system isn't marked by a fence or a sign. It's marked by plasma. Inside our bubble, the plasma is the solar wind, thin, fast, blown outward by the sun. Outside, in interstellar space, the plasma is something else entirely, colder, denser, left over from the deaths of giant stars millions of years ago. So the one instrument that could tell you directly which side of the boundary you were on was the plasma instrument. And on Voyager 1, it failed. Not at the boundary, not in interstellar space. In 1980, before Voyager 1 had even finished with the inner giant planets. Decades before it would reach the true edge. So when Voyager 1 finally crossed into interstellar space in 2012, the first machine ever to do it, it crossed blind to the one measurement that mattered most. Scientists had to infer the plasma from other instruments, work around the gap, reconstruct the picture from the edges. For 6 years, that was the best humanity had. An incomplete map of the most important boundary in our cosmic neighborhood, drawn by a spacecraft that couldn't see the very thing it was crossing. But here's the part that changes everything. On Voyager 2, the same instrument was still alive, and then things got tense, because Voyager 2 was still years from the boundary. Its longer route had cost it time, 6 years and 3 months longer than its twin. While Voyager 1 was already out there, half-blind, sending back data that didn't fit the models, Voyager 2 was still closing in. The whole question hung on one thing. Would that plasma instrument survive long enough to actually reach the edge? November 5th, 2018. 13 billion miles from Earth, moving at more than 50,000 kilometers an hour, Voyager 2 crossed the heliopause, the boundary between the sun's bubble and interstellar space. And this time, the instrument was awake. For the first time in history, a working plasma sensor measured the frontier of the solar system as a spacecraft physically crossed it. The signal it sent back was unmistakable. The plasma density didn't drift upward. It jumped, by roughly a factor of 20, from the thin, sparse gas of the outer solar bubble to something more than 20 times denser on the other side. That jump was the proof. Voyager 2 was out, genuinely, measurably out. And the moment scientists looked closely at what that instrument had recorded, the celebration turned into confusion, because the boundary was not what anyone had drawn. Here's where it stops making sense. For decades, the textbook picture of the heliopause was simple: a clean, sharp wall. On one side, the solar wind. On the other, interstellar space, a line. That's not what Voyager 2 found. Before the spacecraft ever reached the boundary, its instruments detected a whole region, a plasma boundary layer roughly 1.5 astronomical units wide, sitting just inside the edge. That's over 200 million kilometers of transition zone that wasn't supposed to be there. In it, the plasma slowed down, heated up, and grew about twice as dense as the plasma behind it, as if the solar wind was piling up against something, like snow piling up in front of a plow. Then deeper in, a second, much thinner layer. And only then the crossing itself, the true heliopause, which the spacecraft punched through in less than a single day. So the wall wasn't a wall, it was a coastline. Layered, structured, messier and far more complicated than the clean line in every diagram. And that was only the first surprise. Scientists thought they had an answer for where the boundary should sit until they compared the two crossings. Here's the setup. The sun goes through cycles. Sometimes it's loud, throwing out a fierce solar wind. Sometimes it's quiet. And a louder sun should inflate the bubble bigger, like blowing harder into a balloon. A quiet sun should let it shrink. Voyager 1 crossed the boundary at around 122 astronomical units from the sun. Voyager 2 crossed at around 119. Two different spacecraft, two different directions, one heading roughly north, one heading south, two different points in the sun's cycle, years apart, one when the sun was more active and one when it was quieter. The boundary should have been at noticeably different distances. It wasn't. The two crossings landed almost on top of each other, and the mission's own scientists said it plainly. They were surprised, and they could not fully explain why the edge of the solar system would sit at nearly the same distance regardless of what the sun was doing. Think about what that means. One of the most fundamental relationships we assumed, that a stronger sun means a bigger bubble, didn't show up in the data the way the models demanded. We built our picture of the solar system's edge on that assumption. And the two only machines that have ever actually been there quietly disagreed with it. But even that isn't the strangest thing Voyager 2 sent home, because the plasma instrument didn't just confirm the boundary existed, it measured what was on the other side, directly, for the first time. And the interstellar medium, the space between the stars, the stuff scientists had modeled for decades, came back hotter than expected near the boundary. Let me be careful here, because this is where credibility lives. Hot, in plasma physics, doesn't mean it would feel hot. The gas out there is so thin it would feel like nothing at all. Temperature, for a plasma, is really about how fast the particles are moving. And near the heliopause, those interstellar particles were moving faster than the models had predicted. The region wasn't calm and uniform, it was variable, restless, alive in a way no one had directly confirmed before, because no one had ever had a working instrument out there to check. For 6 years, scientists had been estimating this from theory, because Voyager 1's plasma instrument was dead. Voyager 2 replaced the estimate with a measurement, and the measurement didn't match the estimate. That's the pattern that keeps repeating in the story. Every time we finally measured the edge, instead of guessing it, the edge turned out to be stranger than the guess, which brings us to the discovery that the mission's lead scientist called the most remarkable of all. The heliopause leaks, not as a metaphor, literally. The boundary between our solar system and interstellar space is not sealed. It is not a hull holding out the ocean. When scientists looked at the particle data from both spacecraft, they found material crossing the boundary, in both directions. Voyager 1, on its approach, had seen signs of interstellar particles pushing inward, slipping into our bubble from outside. Voyager 2, approaching from a completely different direction, saw the opposite leak, a trickle of particles from inside the heliosphere slipping outward, escaping into interstellar space before the spacecraft had even finished crossing. 2 spacecraft, 2 directions, 2 different leaks, same conclusion. The edge of the solar system is not a wall. It's more like a shoreline with surf running both ways. Our sun's material washing out, the galaxy's material washing in, mixing at the boundary in a way that appears in no model built before these crossings. The mission's own project scientists described the heliosphere as a ship and said, in effect, that the hull is somewhat leaky. Sit with that for a second. The protective bubble that shields our entire solar system, the barrier that helps hold back a fraction of the radiation and high-energy particles pouring through the galaxy, is porous, which opens a new and frankly unsettling question. If the boundary leaks inward, what exactly is getting in? How much? And does it change over time as our sun drifts through different regions of the galaxy? Through denser clouds, thinner clouds, environments we've never been able to sample from the inside? No one can say for certain. And here's the hard part. The only 2 instruments in the universe positioned to keep answering that question are running out of power. Which is exactly why, right now, someone at NASA is writing that irreversible command. Both Voyagers are powered the same way. Not by solar panels, which are useless this far from the sun, but by the slow radioactive decay of plutonium. Steady, predictable, and relentless. Every single year, each spacecraft loses about 4 watts of power. That number never improves. It only ever goes down. To stretch what's left, the mission has spent years making brutal choices, turning off heaters, shutting down systems, and switching off science instruments one by one, knowing each command may silence a piece of interstellar science forever. And here's a correction to a story you may have heard elsewhere. That historic plasma instrument on Voyager 2, the one that made the whole 2018 crossing possible, is no longer running. After it did its job, engineers switched it off in September 2024 to conserve power. Its greatest measurement is already in the books. It doesn't need to be on to have changed the textbooks. Then, in April 2026, the mission crossed another line. Engineers shut down an instrument on Voyager 1 that had been running almost without interruption since 1977, nearly 49 years. The team is now, in their own words, out of easy moves. So they designed a hard one, the Big Bang. Officially, it's a coordinated swap, turning off a group of older, power-hungry components all at once and switching to lower power alternatives. Just enough to keep the spacecraft warm enough and running long enough to hold onto a science instrument into the 2030s. The name comes from the all-at-once part. And that part is the whole gamble. Normally, you'd never reconfigure a spacecraft's power like this in a single stroke. You'd change one thing, confirm it worked, then change the next. Safe, slow, reversible. They can't do that here. Because during any power reconfiguration, there are in-between moments. States where the system is neither in its old setup nor its new one. And in those moments, the spacecraft's own automated safety systems can panic. If they sense the power draw creeping past what the generators can supply, they start shutting things down on their own in an order the engineers can't fully control. So the entire point of the Big Bang is speed. Make every change simultaneously. Sprint through the dangerous middle before the spacecraft's own reflexes can trip. Now layer on the distance. Every command takes more than 19 hours to reach the spacecraft. Every response takes more than 19 hours to come back. A single round trip, send a command, learn what happened, costs the better part of 2 days. There is no live control, no joystick, no undo. You send the sequence, and then you wait, staring at 19 hours of silence, knowing the outcome has already happened out there in the dark. You just can't know it yet. That's the command being written right now. And here's the detail that turns this from an engineering story into a genuinely tense one. They're testing it on Voyager 2 first. Not because Voyager 2 matters less, because it's slightly closer to Earth and has a little more power to spare, which makes it the safer test subject for a procedure that has never been attempted before at this distance, on hardware this old, this far away. Voyager 2 is the trial run. The plan is to work through the Big Bang on Voyager 2 across mid-2026. If it holds, if the safety systems stay quiet, if the new configuration delivers the power savings the calculations promise, then, and only then, the team will attempt the same fix on Voyager 1, no sooner than July. And if that works, there's even a chance that the instrument they switched off on Voyager 1 in April could be switched back on. So everything cascades from one machine. The twin that launched first, the twin that visited every giant planet, the twin whose plasma instrument survived long enough to rewrite what we know about the edge of the solar system. Voyager 2 goes first, and Voyager 1's future rides on whether Voyager 2 survives what happens to it first. One command, no second try. 19 hours of silence before anyone on Earth knows if it worked. Now step all the way back, because the stakes here are bigger than one spacecraft's battery life. When these two machines finally go quiet, and they will, whether from the Big Bang, from the slow decay of their plutonium, or from some failure no one predicted, something ends that doesn't come back for a very long time, there is no replacement. There is no follow-on mission cruising toward interstellar space right now. There is no instrument within tens of billions of miles of where these probes are, and there won't be for decades. The mission's own scientists have said plainly that the Voyagers will likely be the only probes sampling this region for at least the next 25 years. Think about what that means for the leaky boundary, for the wrong-shaped wall, for the distance that doesn't match the models. Every unanswered question these spacecraft raised about what's crossing into our bubble, about how the edge really behaves, about the true nature of the space between the stars, freezes in place the moment the last instrument goes dark. The map stops updating, and it stays frozen until some future mission, one that isn't funded yet, isn't designed yet, isn't approved yet, eventually makes the same journey and arrives at the same frontier, a journey that itself takes decades. Here's the human part most people never picture. The team keeping these machines alive is small. It has always been small. The original engineers have largely retired. The people who replaced them had to learn programming languages and design philosophies from an era before their own careers began just to speak to these spacecraft in the only language the spacecraft understood. That knowledge doesn't live in a modern textbook. It lives in a specific group of people, in a specific building, carrying skills that can't be fully reconstructed from documentation once the last person who holds them walks away. They are still there, still sending commands across 13 billion miles, still waiting 19 hours for the answer to come back. And one of them has captured the feeling of this entire phase of the mission better than anyone. The project scientist has said, in effect, that every day out here could be their last, but that any day could also bring another revelation. That is where we are right now, in 2026. So let's close the loop we opened at the very start. The command being written at NASA, the one that can't be recalled, the one that takes 19 hours to arrive, the one they call the Big Bang, isn't a last-ditch panic move, it's a calculated bet. A bet that a machine launched before the microchip revolution, a machine that went to all 4 giant planets, a machine whose one surviving instrument already broke our models of the edge of the solar system, can survive one more reconfiguration. Long enough to keep listening, long enough to keep mapping the one frontier we cannot reach any other way. Long enough to turn a few more of those baffling, unexplained measurements into answers before the signal fades for good. If it works, we get more time at the edge of everything. If it doesn't, the map goes quiet for a generation. And the signal is still coming, faint, stretched thin by distance. More than 19 hours old the instant it reaches us, but still coming, across 13 billion miles of dark, from a place nothing else we've ever built can reach, for now. If this shook you, subscribe and turn on the bell, because the result of the Big Bang test on Voyager 2 is coming, and when NASA confirms it, whether it worked or whether we lost more than we hoped, that's the video you'll want to have understood before watching. And if you want to know what happens when Voyager 1's turn comes, whether an instrument that's already been switched off can actually be brought back from the dead 13 billion miles away, watch this next. The signal is still coming. The question is, how much longer we'll be there to hear it?